All right, so good afternoon, I guess. It's noon. Today I'm going to tell you about the work we've been doing at HP on benchmarking and designing computer systems for energy efficiency. My name is Mehul Shah, and a lot of this work was done with a variety of colleagues in the past, and I can't name them all, some of whom are actually in this room over here. The subtitle of this talk is How to Break a World Record in 30 Days, and hopefully you'll be inspired to do so at the end of this talk, and you'll know what that means by the end of the talk. So who am I? Okay. I actually got my PhD from UC Berkeley just over half a decade ago. I was working on fault tolerance and load balancing in telegraph CQ. Those are lots of words there, but basically I was trying to make a data stream monitoring system really, really robust. Okay? And so I was a guy that was working in the database group there, but also was working with computer systems a lot and understood a lot of their characteristics. And as a result, HP, which didn't at that time really sell any databases, decided to give me a job. And since then, I've been a research scientist at HP. Okay? One of the things that I want to do is sort of get you guys all excited about HP. Okay? It's actually a wonderful, wonderful place to work. One of the reasons I like it so much is because it's got people from all over. Right? You've got mechanical engineers there, you've got electrical engineers, you've got quantum physicists there, and you have computer scientists over there. And if you ever want to get anything done, you don't ever have to actually go to a library. Right? You just go find the person you want, tap them on the shoulder, and be like, this is what I need. And that's a fabulous, fabulous thing. I know there's sort of really hot places to go these days when you get a job, but none of them have the breadth and depth that I think HP does. So my interests span from energy efficiency in computer systems to distributed systems and databases. And what this lecture is a sampling of all the fun that I've had in the past 5 years and all the stuff that I've learned. So I'm happy to answer questions. Please interrupt me if you have any questions. I want to make this sort of an interactive thing so you understand what's going on rather than me zipping through 50 minutes telling you about what I know. Okay? Good. All right, so what am I going to try to do today? Today, the first thing I'm going to try to do is convince you that power is actually the key problem in computer science today. Right? It's the key. Power and energy are the key things to optimize for, and it's no longer an era about optimizing for performance. Right? It's not about just making things faster. It's about making things more efficient. The second thing I'm going to tell you about is about a benchmark called JouleSort. Right? It's a benchmark that was designed for us to understand and sort of evaluate how to design efficient machines. Okay? And then after I tell you, that's going to be the bulk of the talk, and then after I tell you about that, I'll tell you a little bit about what we're doing now, what's after sorting. Okay? At the end of this talk, the goal, hopefully, is that every one of you will be inspired to go work in this area. It's a brand new area. You don't need to know, stacks of equations or related work and all this stuff to actually make a difference. All of you, I think, can start today if you wanted to make a difference in this area. So hopefully you'll feel that that's true after I've given this talk. All right, so take a few seconds to look at the cartoon. Power is the key problem in computer systems today, ranging from mobile handhelds to laptops to desktops to data centers. Okay? This is a little allusion to the Spider-Man thing. Most of you got it. Okay. All right. So mobile devices, right? Everybody knows that these devices are constrained by the batteries that they have in them. The batteries determine how long they're going to run, right? The batteries determine how usable they are, because when people actually design these devices, they design them around the power constraints that are available to them. So they're going to, only allow a certain amount of functionality on the device based on the kind of battery that's going to be in there. So power, batteries in these devices also affect the usability of these devices. And what's happening more and more today, you guys might already know about this, is all the stuff that you used to find about 5 years ago, MP3 players, phones, PDAs, and laptops, all that functionality, all the stuff that those things do, are now sort of converging into single devices. So what does this mean for power? What it's actually doing is it's actually putting a lot more pressure on the folks that are designing these systems to make them more efficient, because you can't get all of that stuff into these small little packages. Okay, so power is really important in this environment, in this context. It's also important in the data center context, where we have racks and racks and racks of machines out there. Okay, so why is it important there? Well, one obvious reason why it's important is because it affects the running costs of these machines. It affects the amount of electricity that these machines use. But that's not all the whole story. The more electricity these machines use, the more power they consume, the hotter they get, the more cooling you have to have for those machines. So it affects the air conditioning costs. It affects the cost for blowing air, the fan costs, and also all the equipment that goes in these data centers to provision for the amount of cooling that's in there. That equipment is very expensive. Even if you sort of spread that cost over many, many years, it's still very expensive. And so that sort of entire sort of framework around cooling these systems ends up being another sort of majority of the 50% of the costs. So those are sort of direct costs that are associated with power in data centers. Other sort of indirect costs are reliability, right? Systems, if they're not cooled properly, will end up being much, much less reliable. They'll fail more quickly. So when you replace them, you end up paying more for the hardware, right? Because there's sort of a limitation on how much power that can be delivered to individual racks. If your computer systems use up more and more power, your racks in your data center are going to go empty. And so it affects density, how many machines you can actually put in a data center. And the fewer machines or the more machines you can put in a data center, the more stuff you can get done in a data center. So it affects your scalability in the data center. Okay? So it's a problem. But power is a problem for both mobile devices, handhelds, laptops, and for servers, the big machines that run, your YouTubes of the world, your, Gmails of the world, and so on. So how much electricity are we using? Turns out in 2012, all the servers in the US are going to use about 191 terawatt hours in a year. That's basically the same amount of electricity Mexico used 2 years ago. And this is just for the servers in the United States. So that's a lot. So what does this mean? Okay, so this is a graph that is actually showing you two things. There's gold bars that shows you how much people are spending in buying equipment for data centers every year, right? The x-axis is year. And on the y-axis, it's showing you the amount that was spent. The green bars are the amount that was spent on power and cooling. The gold bars are the amount that was actually spent for the servers. You'll see that the green bars are getting higher and higher and higher, and now it's 2009. Soon what's going to happen is the green bars are going to be larger than the gold bars. Right? So we're going to be spending more and more money, more money on power and cooling than it takes to actually buy the machines. We've spent nearly $40 billion this year on. Go ahead.
Is that because power and cooling is just more expensive as a commodity, or because the intricacy of the power and cooling has had to expand? The intricacy of the number of devices and ability to.
So it's actually something slightly orthogonal to that. We're putting more machines in there. The machines themselves are consuming more power, right? So that the power costs have stayed roughly the same, but we're just buying more and more machines, and each of the machines are taking more and more power. So at some point, that's going to have to stop, right? Oh, there's also a slight other trend, which is that the machines themselves, the components themselves, are starting to get cheaper and cheaper. Yeah. All right, so if you don't believe me, trust folks that actually are running data centers today. Google, Microsoft, and so on, all the guys that actually run data centers are already saying that today the cost for power and cooling is more than the IT equipment that it supports. So it's a problem for both data center operators, and the executives that run these companies are also worried. Okay? So there's another sort of higher level problem, right? And that is that all the power that goes into powering all these servers emits carbon. And the IT equipment around the world, it emits about 3% of the total carbon footprint. Okay? Or will emit soon about 3% of the total carbon footprint. Now, that doesn't sound like a lot. But if you compare it to other industries, for example, the airline industry, it's about the same. Right? And the airline industry uses millions of gallons of fuel every year. So this is a little video that kind of puts, it's not my video, it's from EcoSpot, but that puts sort of the entire problem into perspective and how this relates to the whole global warming today. So, we're putting a lot of carbon out there. This is our chance to actually, as computer scientists, as technologists, to start helping with the problem, right? And yeah, 3% isn't a big number right now, but that 3%, all the equipment that we use today, is going to be used to actually figure out how to bring the carbon footprint down for all the other technologies that are out there today. So we can't be egregious wasters, or just as egregious wasters as the other technologies are, okay? All right, so the next question is, how much better do we need to do, right? People are spending a lot of time, a lot of money figuring out how to make data centers more efficient. You probably heard about Google trying to build a data center in Oregon, and Microsoft putting a data center in Chicago and trying to get efficiencies out of there. So how much better do we actually need to do? How much better can we do? It's a good question to ask, right? Because if we're close to our optimal, then we can't do anything and we're hosed. So let's try to figure that out, right? This kind of shows you roughly how much power various sizes of machines use. Handhelds take about a watt, right? So my iPhone here takes about a watt. Notebook here takes somewhere between 20 to 30 watts. Your desktop at home, when it's running, takes, I don't know, between 100 to 200 watts. Depends on if you're a gamer, because then it can go really, really high. If you're not a gamer and you just kind of use it for Windows, well, yeah, different. Servers and data centers take somewhere between 250 to 1,000 watts, depending on how they're configured. The point here is not the exact numbers, but just sort of the variance, right? We've got machines that are basically 3 orders of magnitude, about 1,000 times different from the lowest to the most egregious wasters. Okay. So how does that compare to say, well, let's say we wanted to try and power all these machines using solar energy, right? Let's take a little swatch, maybe the size of a watch, and try to figure out, or the size of an iPhone, try to figure out how much energy you'd get if you decided to, use current technology to power it. Your back of the envelope calculations over here basically show that you're going from the sun, you'll be able to get about 10 milliwatts. This is 1,000 milliwatts. You're a factor of 100 off. You're nowhere near close to do this, getting this done. What about using human energy? This is actually a cute one. Starner from IBM actually estimated how much energy you could harness from, say, breathing, or from just the inherent body heat that you emit, finger motion and footfalls and so on. But except for the footfalls, basically when you're running, the amount of energy that you're emitting is fairly small. You're still less than half a watt. And then there's some famous physicists back 20, 30 years ago that actually thought about this problem early on and tried to figure out, what's the best we can do? And Feynman is one of them, right? And he started thinking about, well, if I had to use atoms to go and do all my operations, what's sort of the minimum energy it takes to do operations? How many operations can I actually get done in a watt? Turns out, roughly 10 to the 18th is the answer. What is that? That's about 1 billion Pentiums for the amount of power that a handheld uses. So what this means is, if we were to get to our physical limits, there's a lot of room there. Okay? There's a lot of room to improve. So this is our task, right? Let's figure out how to improve it. All right, so how do we know that we're done? How do we know that we've actually made things better, right? If you look at a server, it does something completely different than what my handheld does. So if I took my server and I took all the stuff that's running on my server and put it on my handheld, have I made things better? All right, the things that are going to running on my server are probably not going to run as fast. They're probably going to not even be able to run on my handheld. So we actually need a way of evaluating how well we're doing. And the only way we can do that is to actually have benchmarks that evaluate the energy efficiency of systems. Right? We still want to get the same kinds of things done. We just want to do it with less power. So a little background. We're going to need just a couple of equations to understand the rest of the talk. Right? The first thing that I want to kind of define is what is energy efficiency. Before I define what energy efficiency is, I kind of want to define what energy is. Energy is basically the thing that sort of the nature's currency, right, for getting work done. And the way we express energy is as a product of power and time. Power is basically what you get from the electric company, and time is how long you use it. Okay. Energy efficiency is basically getting some task done, some amount of work done for some unit energy. So it's the ratio of the work that you got done for the energy that you put in to getting it done. A little mathematics shows you that that's the same thing as work done over power divided by times time. And that's the same thing as performance over power, right? So if you look at work done divided by time, that's a rate. That's how fast you're doing something. How fast you're doing something is the same thing as performance. And then the power is the denominator. So energy efficiency really is the ratio of power to performance, or rather performance to power. Energy efficiency equals this ratio, the division of performance over power. Performance is work done divided by time. So I'll give you units in a second, and that'll make a little bit more sense. So the units for power are watts. The units for energy are joules. 1 joule is 1 watt second. And the unit for energy efficiency actually depends on the application that you're doing, right? So if you're driving a car, it makes no sense to power a computer, because the computer is going to be useless when you're driving a car. So energy efficiency really is in the context of the thing that you're doing, right? So one measure of energy efficiency, for example, when you're driving a car, is miles per gallon. The miles driven is the work that was done. The gallons of gas that you consume, right, is the energy you consumed. If you're looking at a processor and just looking at the instructions that particular processor runs, then an energy efficiency metric just for that processor might be MIPS per watt. MIPS is millions of instructions per second. Okay, so that looks much more like the performance over power ratio that I talked about a little earlier. Ignore the latter one for now. All right, so now I get to tell you a little story about JouleSort. So we know what we've defined what energy efficiency is, but it doesn't make sense unless there's sort of an application, a workload, right? So let me tell you the story of JouleSort. So there's me. I'm sitting there in my lab, thinking away, thinking about how I can solve my problems for my company. And a bright young graduate student, Susie, comes and she goes, "I want to save the world. I want to make computers energy efficient." And I go, "Huh? I'm not sure how you're going to save the world, but if you want to make things energy efficient, mighty benchmarks will save the day, all right? So you're going to need benchmarks, otherwise you're not going to be able to do it." And Susie, who's really smart, says, "Oh, if I have to make a benchmark, I'm going to have a workload and a metric, right? We're going to have to define both of these things, and the workload is going to define the thing that we're doing, and the metric is going to be the measure for knowing whether we're doing it well or not." So before we started, there's all kinds of confusion in this field on what the right metric was. There still is a little confusion, but we hopefully helped sort some of it out. People were saying, "Oh, you look at a machine, just look at MIPS per watt, that's all." or look at a machine, just look at how much power it uses, and just, that should be enough. The problem with all these approaches, well, there's sort of three main problems. One, the previous approaches were often focused on one specific component of a machine, like the CPU, and sometimes that's good. Sometimes that's not enough, right? Not all machines are just CPU. Sometimes there's a lot of disks there. Sometimes there's a lot of memory there. Some of these benchmarks were out there were just underspecified. They kind of said, just measure the power, measure something else, but they didn't tell you what workload to run. They didn't tell you what to run on the machines. So you could just turn the machine off and be like, look, I'm doing really well. And then some benchmarks were actually specified, but they're really, really particular, right? They said, well, you got to run Java, and you got to run this thing, and you got to run that thing. And that's really good if that's what you're doing, right? If you're running an application server or running a database, then that's what you ought to run. Unfortunately, it's not a good way of trying to evaluate the energy efficiency of a wide variety of machines. What we really wanted was a simple benchmark, a very simple one, that would measure the energy efficiency of an entire system, or an entire machine. So that's what we mean by holistic. And that's why we came up with JouleSort. And it really wasn't entirely our idea, right? Let me tell you what JouleSort is. It's not a benchmark that's designed for people to say, okay, if I want to buy my next machine, I should run JouleSort on it. And depending on how much efficiency there is, the better the machine, the more appropriate it is for my company. It's really not that kind of benchmark. It's a benchmark for people to experiment with, right? For people to try out a whole bunch of different things and kind of get an idea, kind of get a sense for how efficient that thing is. One of the things we like about it is that it's easy to set up and experiment with. There are other benchmarks in the database community that are based on sort as well. There are performance-oriented benchmarks that say how fast you can sort, or price-oriented sorting benchmarks that basically evaluate how cheaply you can sort, but that's really about how cheaply you can sort with the hardware. It doesn't include the power cost. And those benchmarks were often technology bellwethers. When somebody would go and take that benchmark and evaluate a new kind of machine and say, look, this is the best machine, this is the fastest machine today for doing this, those machines ended up being the machines that the industry adopted a few years later. Okay? So it was a good way for them, with this sort of workload, to evaluate various disruptive technologies. People used to use mainframes, then they went to supercomputers or shared memory machines, then they went to clusters. And right around those transition periods, you always saw a sort benchmark winner that came around with that particular type of hardware. So we're hoping that if we had a benchmark around sorting, but for energy, we get people to think about the kinds of machines you would build to make things energy efficient. Okay, the kind of computers you'd build to do it, and systems you would build to do that. So we were the first guys, I believe, to build a benchmark that was a whole system energy efficiency benchmark. We specified a workload, a metric, and the guidelines for actually running the benchmark. The workload was external sort. So everybody knows, you all learned at some point, I hope, how to sort data on a machine, right? Yes? No? I see nods. Yeah, heads nodding. Okay, great. All the sorting that you might have done in the past has been where you take your entire data, stick it in memory, and then you pick your favorite sorting algorithm: quick sort, bubble sort, merge sort, and whatnot. Well, the database guys years ago figured out that you could actually sort things that were even larger than memory. And the way they would do it is they would shovel things back and forth from disk, right? Sort those individual pieces, and then merge all those things later and have a final sort. So that's what external sort is. And that's what JouleSort is based on. Okay? So why external sort? Why is this a good benchmark? So it turns out when you run external sort on any system, it tends to exercise all the components in a system: the processor, the memory, the disk, the I/O subsystem, the system that brings in the data from the disk to the memory, the operating system, and the file system. And it tends to exercise these components in a fairly balanced way. Another reason we like sort, external sort, is because you can actually get it running on a variety of systems, from PDAs to laptops to supercomputers. And we have gotten it running on PDAs, laptops, and supercomputers, right? Turns out today, a lot of the stuff that we do is around information processing. And information processing requires you to do a lot of I/O. And external sort is representative of a lot of I/O-bound tasks, or a lot of, not I/O-bound tasks, excuse me, a lot of sequential I/O tasks. And you would find these kinds of tasks in data warehousing, business analytics, when you're trying to figure out, whether a particular, whether a particular sales cycle was good or not. It's useful for, counting web clicks, recommending movies, if you're into Netflix, and so on. Another reason why we liked it is because it's hard to cheat. When you sort, you got to sort, right? There's no sort of end around to it. Yeah, there are better algorithms and worse algorithms for it, but you've got to sort the data. And you end up measuring the system while it's doing useful work, rather than while the system is actually just sitting idle. Okay. I already told you about the why we like sort, because it's sort has been a technology trend bellwether in other contexts. And then finally, it gives us a way to measure the system's energy efficiency in sort of a holistic way. If it turns out that you make some improvement to the CPU and it makes no difference in power consumption, or it makes no difference in the performance, then maybe you shouldn't be doing that. If you make a change in, say, how memory works and it makes a big difference, then maybe you should be doing that. But at least it gives you an entire picture rather than just individual components. So here are the benchmarks that already existed before we proposed JouleSort. And they basically fall into two categories. The ones that say, go really fast, pure performance. And they're minute sort and terabyte sort. And they're the ones that say, how much can you sort for very little money? If I give you a penny, how much data can you sort? And that's sort of the most famous one. All right? So what we did is we said, well, we should have a sort like that. And the problem with building JouleSort in the same way as the other sorts is there are ways to cheat if you built them the same way. So Susie, who's really smart, says, no, we can't build it the same way, because if you build it the same way as you built the other two sorts, people can cheat. So you should make sure that you actually allow for all kinds of systems to be measured, and you should make sure that these guys can't cheat by turning the system off, for example, and still get a good number. And so after a lot of arguing between Susie and I and Susie and other folks, and we came up with this sort of formulation. There are three categories: 10 gigabytes, 100 gigabytes, and a terabyte. And in those categories, the winner is the sort that uses the least amount of energy. Okay? Now remember, I told you that energy efficiency is the same thing as performance over power. Well, we like people to actually report their winning entry in terms of sorted records per joule, because that's the performance, the amount of records you sorted. That's the amount of work that was done, the amount of records you sorted, divided by the energy, right? And the reason we like it is because it looks like miles per gallon for a car. So the bigger the number, the better it is. Okay, good. Obviously, these categories are going to have to change. Right now, they're kind of designed for the sort of small-end laptop-style machines for the low-end, desktop-style machines for the middle, and sort of big, clusters of machines for the high-end. But as computers and machines get faster and better, we're going to have to move these categories along. And in fact, we're thinking about doing that next year. There are two actually orthogonal categories in the size categories in the sort benchmark. They're already there, and we just borrowed them. One is Daytona for a sort that is something that is sold and supported, right? And uses basically commodity off-the-shelf components. And then there's the Indy, where you can do whatever you want, right? You can design your own hardware. You can, do whatever you want. All right, so then we actually came up with rules for how to measure the system. And when I explain this, hopefully you guys won't be sort of, you guys will feel like that you can actually do the measurements yourself, that you don't need a double degree to actually do it. First, you need a power meter to measure the power, right? Most things that you measure, typically in computer systems, is about just measuring the timing. In this case, you need to measure both time and power. So you need a power meter. You can buy power meters that plug straight into the wall. So that doesn't take a lot of brain power. I think we all know how to do that, right? These power meters also have plugs in them that allow you to actually plug in the system that you want to measure. Okay. So once you have that, you have actually something that's taking these readings. And then you need a monitoring system on top that talks to the power meter over the network, and talks to the system that you want to measure. And it gets the readings from the power meter, and it gets the sort of the timing information and job scheduling stuff that it needs to do to start off the sort from the system that you're measuring. And for each of these things, we have little rules. One rule is that you got to measure energy of all components. So, if you've got a little network inside of your machine, or you got a little battery inside of your machine, you have to measure the power of those components. So if you have a battery, you have to account for the potential energy in the battery and how much it was drained. If you have cooling devices, you got to run those. And the rule is that you got to run the system, somewhere between 20 and 25 degrees Celsius. And the reason is most systems have to operate within some sort of environmental range, and this seems to be the range that keeps them fairly reliable. For the power meter, there's all kinds of little, technical specifications to make sure that you actually are measuring the true energy. It's not important for this talk, so I'll skip it. And then for the monitoring system, one measurement isn't enough. There's a lot of variability in the amount of power that's used and variability in the timing. So we ask you to take at least 3 measurements, take an average, and report the average and the confidence. And if you want to reduce the confidence, take more readings. All right, so we go off with this benchmark, armed with this benchmark, and we looked at a bunch of existing systems. The top system is actually the penny sort winner from, I think, 2007 or 2006. 2006, and it's an estimated value. We just kind of estimated what it would be because we didn't have the system in hand. And then these are the systems that we measured in-house. The systems in black, one is the low-power blade. It's sort of a blade in a blade enclosure that you would put into a rack. And then you'd have a low-end server. And both of these systems, if you compared it to the GPU TerraSort, which was the penny sort winner, look horrible, right? 300 sorted records per joule in the column at the end, and 1,200 records per joule in the column at the end. And then we measured sort of a modern laptop and a balanced file server that had a lot of disks and sort of a moderate-sized CPU in there, right? It was an Intel Xeon. And they were about the same, or a little bit better, than GPU TerraSort. So these are the two we focused on. But they were drastically different machines, right? This guy has one disk, and it gets 3,400 records per joule. And this guy has 12 disks all working together to get 3,800 records per joule. Why do you think that they're about the same in terms of records per joule? That's right. Right? This thing goes fast. This thing goes slow. But over here, this thing's only using 20 watts, and this thing is using 400 watts. And it turns out that ratio, performance to power, puts them around the same range. All right, so then we said, OK, let's see if we can make them any better. And the first thing we said was we're going to try to make all these things really energy efficient by turning off the machine when we didn't, and so on, playing tricks in the software. And we kind of looked at sort of how much power the system took when it wasn't running anything. Just it was active, the operating system was running, but it was running the idle thread. And the power only dropped from 406 to 370 watts. It didn't drop much, right? About 10%. So that wasn't going to help a lot. And then we looked at it, and we said, OK, well, this thing is actually, half of the power is going into the CPU and the memory, and the other half is going into the disks. So maybe we can play with the configuration of this thing and the hardware of this thing to make it better, right? Because we know it's going fast. We just somehow have to figure out how to make it low power, and then we'll get a better number. And so the first step was to pick better components. Instead of using sort of a moderate sort of Xeon processor that went fairly fast and used a lot of power, we dropped the performance by 25%, or kept 75% of the performance, and dropped the power by almost half. So you'll see that we did better on the performance. We kept more of the performance and dropped more of the power, so this ratio improved. Right? Performance over power improved. We did the same thing with the disks. Right? We said we're not going to use these Seagate Barracudas. They use 13 watts. We used a laptop drive. At that time, there were no flash drives that we could actually put into big systems. The SSDs weren't around. And it dropped to 2 watts from 13, so we dropped 85% of the power, or kept 15% of the power. And performance dropped by only half. The second thing we said was, okay, well, it's just changing the components isn't enough. We got to make sure that the system is completely utilized, right? And it turns out that the disks can feed data to the CPU pretty slowly. So the CPU spends most of its time just churning, not doing anything, if you only have one disk. So we added more and more and more disks to the system, and the performance of the thing went up, right? And the peak performance was up here. Okay. And as the performance went up, we added more and more power to the system, but not that much, because there were these little laptop disks. So you see the energy efficiency of the system, and it continues to go up. And it turns out the peak energy efficiency is the same as the peak performance. So what this said was, just get the thing running fast in software and pick the right components. And so, Susie won the first JouleSort benchmark for the 100 gigabyte category. The thing was going about 4 times better than the previous estimated winner, and it only took about 100 watts. So this wasn't very hard. It was just getting components off the shelf, putting them together, and we didn't have to write any software. We just borrowed the software from a vendor that was just giving this away for trial, right? Ordinal Technologies, and you yourself can go and get a trial for a month and try it out. Here's what it looked like. Yes, Susie plugged in all those cables herself. That was... We did it many times. We used a motherboard that was actually designed for... It's funny, this motherboard is designed for gamers that want their gaming systems to be quiet. And so these are the only motherboards that we could find that could take a mobile CPU. We stuck them on there. And they had 2 PCI slots. Those are the slots that allow you to communicate to the disks. And in those slots, we attached RAID controllers that let you sort of communicate to all the disks in parallel, and 13 laptop drives. And if you want more information about this system, it's in the JouleSort paper. You're welcome to download it and take a look at it. Okay. But the trick here was use sort of server class stuff and replace those sort of individual components with lower power components. And we did this about 2 years ago, and now you see a whole bunch of other folks, Amazon, Microsoft, all these other guys for various sort of front-end things. They're starting to take similar approaches. Take away those sort of expensive CPUs and use low power stuff. All right, so that was JouleSort V1. JouleSort V2 is the small story. So what do you think this is about? Let's see. Justin, I didn't have a picture of Justin, but Justin was an undergrad just like you guys. And every undergrad that I've found thinks they're Superman or Superwoman. And they think they can save the world, right? So he goes, I too want to save the world. But he's just an undergrad. What am I going to do with him? So he comes in and said, young grasshopper, you're going to have to take a different path. And so, he does. He says, unlike all of you guys, I have an iPod. He says, I'm going to use my iPod wisely. Okay, so what is this all about? Well, it turns out that we decided to take a look at systems in the first rev that were desktop class systems. And everybody we knew was talking about these guys and how low power they are. But are they energy efficient? That's the question that we wanted to ask. Okay? So we figured that there was a system sort of in this class over here that would give us pretty good energy efficiency. And we went around and looked at a variety of systems and tried to measure their energy efficiency using this benchmark. We started with, we actually didn't try it with an iPod for various reasons, and iPhones weren't out yet. So we tried it with Gumstick. Gumsticks is this sort of little device that's supposed to be put into, it's an embedded device, right? You can put it in robotics. People use them for radio-controlled helicopters and so on and so forth. And so he did this, and it turned out that this device got you 50x better power, right? It only used 2 watts. It was great. Its performance was horrible. It was 150 times worse in terms of performance. Although people had decided to reduce their power of these things, the I/O system, this thing really wasn't designed to do a lot of data movement. And as a result, on the JouleSort benchmark, it didn't do very well. And now you're going to say, well, that's not what it's designed for. And the argument that I'm going to make is, look, this thing is going to be designed to do everything in the future, right? Today, unless I have to give a presentation, I just carry this around. I read everything on here. I do my emailing. I can even do all my editing on here sometimes. So that's the future. And if it's going to be doing data management, it better do it well. And in this benchmark, it doesn't do it. All right, so second device. This is a device that actually is supposed to do data movement. It's used for network firewalls and various network address translation. It goes into routers and homes and things like that. Okay, it's the Socrates board. Well, it did better. Instead of 11,000, it gave us about 6,000 records per joule. The performance was 30 times worse, and the power was 16 times better. So you really want this to be small and this to be large to get better energy efficiency, and that's not happening. Again, the I/O didn't scale. So then we finally got a device that was meant to do real work. Right? It's the VIA Pico ITX box, and it's meant to do video encoding and decoding. It's meant for like set-top boxes, your cable boxes and so on. And here, we first started, we put laptop drives on that thing, okay? And the performance was 8.5 times worse, and the power was 5 times better. So we got better records per joule. And then we actually replaced all the laptop drives. By the time we had got this, we were able to get ourselves some flash drives. And we finally got a ratio that was close. Okay, 7.5 times worse and almost 7 times better. Didn't quite beat Susie's record, but we came close. But he did win the sort of power and cost benchmark, right? Which is if you the Pico ITX and the 2 flash drives attached to it were much cheaper than the JouleSort machine, and it gave you about 9.1 sorted records per joule per dollar. Okay, so here's an undergrad comes in, changed the world. Okay, so I think all of you guys didn't do exactly the same thing. Some of the lessons that we learned. Lesson number 1: all the components matter. Low-hanging fruit. Use lower power. Lesson number 2, current hardware technology doesn't really let you vary the power that much. So, your peak efficiency point is actually your peak performance point. The benchmark does have some limitations. I'm not going to go into them. But one of the things, the biggest limitation of the benchmark, I think, is that you can't really there isn't really much software innovation except for taking the benchmark and rewriting the sort algorithm for a new type of hardware. There's really not much you can do in the software. All right, so let me tell you a little bit about what we're going to do, what we did further ahead. How much time do I have? None. Okay. So then I won't tell you too much about what we're going to do further ahead. We'll skip the software piece. We're looking into ways of designing computer systems that have a lot more components and a lot of more choices so that software can make those choices for you. Okay? A lot of graphs there. Looking forward, one of the things that should be apparent now is that a lot of the power that's going to be consumed in the future is going to come from managing the data that's going to come in the future. Here's Mark Hurd, the CEO of HP, saying, you're going to collect more stuff in the next 4 years than you collected in all the years of history on this planet, right? So one of the things we're doing at HP is redesigning systems with both the software requirements and hardware sort of constraints taken into account together. So there's this redesign or co-design of things happening, and it's around data-centric architectures. And the second thing that's actually going on is it's not just about energy efficiency. I just talked about how much energy that the machines use, right? And it's really about sustainability. And sustainability actually incorporates the entire life cycle of the computer system from its birth to its end. And there's a little clip here. It'll take a half a minute or so. But it's not working. Okay, you can't hear it. That's okay. I'll just explain it. Okay. There's actually energy used to extract the materials to build what you're building, to move it, to manufacture it, to operate, and also recycle it. Right? And turns out that all the other components matter. And if we are going to save the world, we better be worried about those components, right? And that's what we're doing in HP. We're thinking about all of those pieces at the same time, both at the systems level for individual machines and for the entire data center as a whole. And this is a little graph that shows you how much energy right now in a machine, roughly server, goes into operating the machine over its life, the energy for recycling and creating it and transporting it, and the energy that goes into cooling it. And we want to try to take care of both of these pies. And then the rest, there's many more possibilities. Okay. So now I want to sort of recruit you guys. All right. You guys can break a world record. I guarantee it. Find some hardware. I know you guys have some. In your office, in your machine room nearby, go online, look in your pocket, be creative. Pick a simple workload. If you can't pick a workload, I got one for you, sorting. Okay? Go download it. Pick your own if you want. Get a power meter. They're not that expensive. If you really, really are interested, I'll give you one. Okay? Measure its energy efficiency and see how you can improve it. And by the way, tell me about it, because I'm collecting all this information in one place, and then hopefully people will have an idea in that one place on what actually can be done with computer systems. So in conclusion, we talked about energy efficiency and how energy is an important component, both for handhelds and data centers. We're moving from an era of performance to an era about performance per watt, per power. We talked about JouleSort and why it's important, and how there's actually a lot more room for everyone to play. And I encourage you to try. Thanks.